continuously be applied to RLVR as well. We're going to be getting human feedback. So we're going to get a prompt, we're going to get outputs from our model, we're going to get humans to rate those outputs. We're going to train a reward model on those outputs, and then we're going to fine-tune continuously to update our model based on the rewards from the reward model. And we're generally going to take a prompt, we're going to generate from our model, we're going to get a reward for that prompt, and then we're going to update for that prompt. So we're going to focus efficiency-wise on this last piece, this kind of RLHF fine-tuning or RLVR fine-tuning equivalent. And breaking this thing into three pieces, it's really generating a completion, labeling with the reward, and then training on that sample. And the main issue why this is a complicated kind of thing to do is because it's combining two different parts of LLMs, the LLM generation and the LLM training. And as our infrastructure has become more advanced, we're now having separate libraries that are specialized in LLM training, like Hugging Face transformers, and LLM generation, like VLLM. So for those of you that haven't used VLLM before, if you compare Hugging Face transformers to VLLM for generation, the difference is massive. So here's us generating 1,024 tokens across different model scales, like from a couple 100 million to like 7B. And the generation time, as you scale kind of the model size with Hugging Face transformers, is like super exponential. It's awful. And with VLM, it's really not as bad. So at the larger model scales, when you're kind of training a 7B model, it's just infeasible to be using the same library for training as you use for generation. So the reason kind of our synchronous all-policy RL language models is slow is because of the new info. So prior to this work, kind of this was the standard setup that people would use for doing RLHF. You've got two GPUs, you're going to be doing generation on both the GPUs, you're going to be doing training on both the GPUs. And because you're doing the same thing on both GPUs, what you're doing is you're using the same backend for both of these. And that means, your training is great using Hugging Face, but your generation is really slow. And so one way that you could speed this up is you could say, okay, well, let's put VLLM on one GPU, and let's put Hugging Face transformers on the other GPU. So this sort of thing seems like it'd be faster because, well, your VLM is way faster at doing this generation. But now you're training that red bar. Well, you're no longer training on two GPUs. You're training on one GPU, which means it's going to take twice as long. So overall, this ends up being inefficient, especially because each time you're doing your generation, you're not doing your training. And each time you're doing your training, you're waiting for that to finish to do the next generation. So you've got all this empty space that's just idling your GPU. So this work pretty much proposes taking this synchronous RLHF and making it more efficient by becoming asynchronous. What we do is we say, okay, previously we were always training on the outputs that our model gave at that exact step. And we're going to relax that assumption. And instead, we're going to train on the outputs from previous steps. And that's going to allow us to generate at the same time that we're training. We can do both things asynchronously, simultaneously. And then kind of this one step asynchronous, this means that we're at every step training on the previous step, generating for the next step. So this is like, I think the most important part. If anyone has any questions, I think now's a good time to stop and to kind of clarify things. criticize, whatever you want. All good?
Yeah, you're back.
Okay. All right. It's clear to everyone, then yeah, I'll just continue. So the questions that we were asking at the beginning. This question is, what does it mean to train fast? So let's just say kind of we're removing all that empty space in our pipeline. We're using our GPU more efficiently. That's what we mean to train fast. And so what's the right way to do this paradigm? So in this work, we're going to be using a benchmark called TLDR summarization. We've got Reddit posts. We've got the TLDR of those Reddit posts. And we've got human ratings for the better and the worst TLDRs. And then what we're going to do is we're going to train a large reward model. And this large reward model is going to act as our like perfect proxy human so that we get like consistent responses. You can think of this as, sorry, go ahead.
Sorry, Michael. I just had a clarification question. So this is like TLDR from Reddit, right? But I'm curious if this refers to a specific like methodology or algorithm for summarization, or if this is effectively just a GPT call.
So the are you talking about the task or the evaluation?
I'm talking about the task.
Yeah, so the task is like the standard TLDR summarization task introduced by OpenAI in one of their papers. So they just took like a Reddit TLDR summarization data set and then collected human preferences for it. Does that answer your question?
Yeah, totally. I'm going to fish around for that paper, but that's cool.
Yeah, this is a standard task, and the setup that we're using with the gold eval is available on GitHub by me. It's we kind of can then eval against a human baseline, and pretty much the thing that we're measuring for success is saying like how much better is our generated response than the default human response according to our gold reward model, or equivalently you can think about it as like evaluated by like GPT-4, some API. And the thing that we're going to ask is we're going to say, how do we measure how off policy we are? We said that we're not going to train from the data our model itself generated at that step, but we can train on data from many previous steps. So in the standard case, we've got one mini batch. So we generate one mini batch. The next step, we train on that mini batch. And then at that step, we're generating a mini batch for the next step. We can generate two mini batches. In that case, we're training on data from 2 to 3 steps because, we did an update at the second step, and then on that second batch, we're now one more update ahead. So, and then we can generate 3, and we can do 3 to 5. So basically, kind of, we can be more and more off policy as we generate more of these mini batches in each kind of chunk. And when we look at the performance versus the level of off policiness, what we see is a little bit of degradation. So that light green line all the way at the top, on the left, that's our most on policy thing. That's kind of one mini batch off policy. And as we get darker and darker green, we see kind of worse and worse performance, and that's more and more and more off policy. And the second graph is the KL from initialization. You can think of that as kind of the distance from the initial model. It can also kind of correspond to alignment tasks, but we don't really need to think about that. Now, looking at these two graphs, it's not really clear exactly what's going on. But if we plot them against each other, if we plot the performance against the KL, that's when we see something pretty clear. So the most off policy, 64, that's all the way in the bottom left. And as we get more on policy, we're essentially going up along this curve of distance from the initial model and increasing in performance. So it's not that our performance got worse as we got more on policy, off policy. It's the fact that we just didn't progress as much along the training curve. We just didn't learn as many things. We took the same number of steps, but because the data we were taking steps on was older, we weren't making progress. And this isn't a new thing that we're noticing. You know, in OpenAI's 2019 paper on the DOTA 2, they found the exact same thing. So the increasing staleness of the data reduced their training speed. And their whole idea was that we need to train on newer data. So kind of we can re-answer that second question. Kind of, what does it mean to train fast isn't just about using your GPU efficiently, because we could be making training steps that don't lead us towards a better model. It's about achieving performance in less time. So this talk then becomes about how do we balance the recency of our data, the on-policyness of our data, versus how asynchronous we can be to achieve compute optimality for RLHF. And in the paper, we kind of investigate two different losses. We look at PPO, kind of the standard loss. We look at online DPO. We look at RLU, which is kind of similar to GRPO. In general, for our particular use cases, we found this online DPO method to be the most robust to off-policy data. But I think newer works have found that GRPO, RLU, and other similar losses are equally effective at larger scales. But the thing that kind of is more important than what's the best loss in one particular benchmark is the question of how does off-policy scale? Because if we plot each of our little final points for different model sizes, you know, we've got 410 million parameter models in blue, we've got 1 billion parameter models in orange, we've got 2.8 billion parameter models in green. And we plot kind of the different levels of off-policyness. And I've noted here kind of the 16 mini batch, kind of the most off-policy point here. If we look at the distance from the most off-policy point to kind of that cluster of on-policy points, we see that as we scale up our model size, the off-policy points, the points that are kind of training on the most off-policy data, are actually getting closer and closer to the best model performance. So what that means is, as our model size increases, our models become more robust to off-policy data. You can train on more off-policy data and get better training signal as your model size gets larger. So with this kind of all together, if we compare on the TLDR task, and we compare synchronous versus asynchronous, we see that kind of the win rate versus the compute time as we scale up the model size, it doesn't look like much at the smaller model sizes. But as we get to 2.8B, suddenly we're seeing like a 25% gap. And that's only a 2.8B, which is, in the words of one reviewer, very small model size. You know, toy data task. And so this whole thing to say that asynchronous methods are more efficient and they become more robust to off-policyness as our model size increases, which means they're even more important at larger scales. And let's talk about larger scales. Kind of let's train a real large-scale chatbot. We're going to train Llama 3.1 8B on kind of a pretty simple chatbot task. And we're going to compare, you know, the reward under synchronous versus the reward under asynchronous. And what we see is pretty much exactly the same performance by asynchronous as synchronous. Asynchronous is just doing it in less time. And then the KL divergence, the lower KL is actually preferable, but that could just be noise. More importantly, when we look at the final model and we look at the win rate under kind of GPT-4 as a judge, we see the exact same win rate between our synchronous run and our asynchronous run. We see super similar response lengths. So despite the fact that like RLHF is a pretty noisy process, this just seems to work and doesn't really add that much noise. And this is RLHF, but let's kind of, you know, math and reasoning, that's the hot thing right now. So we look at kind of a very standard data set, GSM-8K, and we look at kind of just solving these math problems written in text. And again, we take like a 1B base model, we do synchronous versus asynchronous, and we find pretty much the exact same thing. Our asynchronous run is even slightly better, but again, this could just be noise. But the most important thing is the compute time. You know, it's running in 2 hours versus 3.5 hours, which is just like a huge difference if you're going to be training large-scale RLHF. So, again, now a good time to stop if there's any questions.
I know, you know, your work is primarily one of these methodologies, but if you could, I guess just very quickly talk about what the other models approaches might be. I guess to just give a little bit more of like an explanation, I guess, for why asynchronous online DPO, you know, empirically works. Because I think I understand like the theory of this, like what you showed us, but the other competitors are kind of still a black hole.
What competitors?
So I mean, here, you know, sync PPO, sync RLOO, sync. I mean, these are all synchronous processes, right? Yeah. So I guess like I think the compute time change is kind of obvious, right? But the pass at one is a little bit surprising to me that it outperforms even there.
I mean, I think the pass at one outperforming online DPO, like the async outperforming the sync, to me is just possibly noise. I wouldn't expect async to necessarily outperform sync. Like,
It's very interesting that they're basically the same. Yeah, you're right. I shouldn't frame it as a significant increase. That it totally is noise, but I mean that given any error bars, it's pretty remarkable that there's no real loss.
Yeah, and these results are robust. They've been kind of reproduced in other papers. I think why online DPO over RLU? I think online DPO because it's just getting whether one answer is better, not how much better one answer is. I think you end up getting kind of a little bit more robust of a loss than something like RLU at smaller scales. And this is 1B. So what I've heard is that kind of as we scale up to, you know, past 7B to like 30B, they're kind of having a robust loss isn't as important. Yeah. So okay, my work isn't even about online DPO. I didn't introduce that method. I'm not even kind of necessarily vouching for it. I'm just showing that kind of our best performing method kind of is matched by an asynchronous version in less time. Yeah. All right. Well, then just the last little bit. Kind of those of you that are familiar with DeepRL and kind of might just be saying like, where's the novelty? Because in DeepRL, they've been doing asynchronous, they've been doing off-policy learning forever. It's just been the standard. And if we showed that there's degradation due to off-policyness, and kind of we're making a push to move LLMs in RL in that direction, but the novelty of this work really comes down to kind of that second question. Kind of, should engineering influence research, or should research be influencing engineering? And the reason that this work was novel, the reason that this kind of wasn't done before, is because in some ways research influenced engineering. You know, when I talked to the team at NVIDIA, like why their library was synchronous and on policy, it's the engineers said, well, the researchers told us that they needed an on-policy RLHF algorithm. So we designed a library to be synchronous. And also, engineering affects research. You know, if you're going to go do research on RLHF, and the state-of-the-art library is a library doing synchronous RLHF, well, then the thing that you're going to investigate is going to be an on-policy algorithm. And this kind of relates to, I think, a great paper like the hardware lottery by Sarah. So the real kind of key here is taking insights from both. The idea that for research, an optimal learning algorithm requires recent data from the policy, not fully recent data, just more recent. And from engineering, the fact that if we separate our generation and our training on separate GPUs, we can be more efficient on those separate GPUs. So the goal is that we need to balance the generation speed with the data recency, and we do that best with asynchronous off-policy learning. So thank you again to my collaborators. Yeah, I'll take any questions. I also have some more slides of like follow-up works that have happened since this has been published. Let's see. If no one has any questions, then I can do the follow-up work, but I'll leave like another minute.
A question from Jordan in the chat.
What's considered more recent data? Specifically, the kind of data that was generated by a model close in time to our model. So kind of not 13 updates ago, but 5 updates ago, 2 updates ago. Kind of that thing that I talked about, the off-policiness.
Also, folks, you're more than free to ask Michael questions about his other work or his career direction. This is, like this is incredible work. Don't get me wrong, but he has a lot to talk about. So I guess my question might be, I know there's probably limitations to what you can say, but super curious about like what's it's like on the inside of AI2. And I think you mentioned you were working a lot on the pre-training side. But anything that you'd be willing to share about how you kind of got hired, how what they're doing that you think is interesting or novel compared to other foundation model companies, and like what it's been like.
Yeah. So I'm the way that I started working with AI2. This work was in collaboration with Costas, the second author in the top left over there. So he started at AI2, I think, a little bit before this project got started, and we'd been collaborating for a little bit. I'd been the second author on his paper at Colm last year, and he was just like a fantastic engineer and researcher. And kind of in our collaboration, I kind of learned a little bit from AI2. Some of the runs here were done on AI2 infrastructure, like the large 8B run, because that was difficult to do in academic compute. So yeah, after kind of collaborating for a little bit, finishing this project, I was kind of like, I think I'd like to come to AI2 and implement more things in kind of RLHF, because this project, I realized that I just needed engineering support for my research, and also that I wanted to make sure that my research would actually be used in kind of state-of-the-art models. So I aligned my research direction a little bit with what AI2 was doing at the time, and this async RLHF thing ended up being used for AI2's model Tulu 3 and for their model Olmo 2. So like, it was great that I was doing it at 8B scale, but then they verified that like, oh, you could actually do async RLHF at like 405B scale to train like fine tune on top of Llama. And they even trained kind of their open source model, Olmo, to the instruct version with async RLHF. So I think the reason I wanted to come here specifically is because as a kind of open source and nonprofit institute, Allen AI is doing like everything in the open. This is, I think, the last remaining place building a SOTA language model that is telling you all of the details, that is revealing the data that we use, the code that we use, every single trick, exactly how the pipeline works, like an actual, like, you know, research paper and technical report about this, not just saying like, oh, we got SOTA numbers. And as someone doing like research in a PhD, it's really important to publish. And I wanted to work on post-training and publish, which has just become kind of impossible nowadays. Yeah, I don't know if that answers the question.
No, it absolutely does. Also kind of curious where your open source kind of values come from. You know, I work in industry, so I would love, but my background was originally in research. I wanted to do a PhD. You know, did some crappy, you know, IEEE papers, but yeah, I guess you know, for me, most of the code that I've done is locked in, you know, some enterprise GitLab, and will never see the light of day. So curious, you know, why you decided like this direction or this set of values, and when did that happen?
I mean, I think you know, I started not in research, but in software engineering a long time ago. And before that, like I was, you know, the way I learned to do code is by installing Linux. So this is just something that I've like been doing for a while, open source. I'm currently on Linux, on the only person at AI2 using a framework laptop when everybody else has a MacBook. So I'm, I guess, really hardcore on that open source stuff. But in terms of research, I think that open science is something that's super important. One of the reasons that we've made such good progress, I think, in deep learning for the past kind of so many years is because we've been sharing that information. Like you look at kind of the ping pong of the top papers and kind of the big research shifts, they've been happening not at any one individual lab, they've been happening in between labs and kind of through different academic institutes. By sharing this information, like people can work on pre-training and actually validate the things that they're doing at real scale. Because currently, you know, like I think the only other lab releasing like real details of what they're doing for post-training is Cohere. And it's not easy as someone working in academia to realize, like, is your research actually impactful? Is it actually useful if you don't have all the details? So I think that we will make a lot better progress towards better algorithms, towards better methodology, if we're being open in this way. I do think it is kind of like a rising tide raises all boats type of thing. There's still a lot of progress to be made in these, and we're kind of maybe a little bit early in closing down the tightening up on kind of the sort of things that we're doing.
I had a query regarding since you have used Python for training, you had something in the paper regarding GIL, Global Interpreter Lock. So yeah, did you manage to get past that?
We did, yeah. The asynchronous code was like really shoddily written by me, and then later improved by Costa to be actually good. But when it was very badly written by me, it was just like very basic Python multiprocessing stuff. And so we were getting some random slowdowns We thought this might be because of the global interpreter lock, but we weren't sure. We then later switched to Ray to do the orchestration of like putting training and generation GPUs, and that kind of got rid of everything. I think nowadays people are moving to pure PyTorch ways of just using Torch distributed to move things on different GPUs, and that solves everything.
Yeah. And the other query that I have is like for scaling up with asynchronous RLHF, you used PPO instead of online DPO. So is there a reason that?
No, we use both. In our paper,
Okay.
we use both.
Okay.
Nowadays, everybody is doing modifications to gRPO. And kind of people have built on top of our work to be even more asynchronous and deal with some other issues. But I don't see a lot of people using value models, so it is a lot of like Arlu gRPO style methods.
Oh, okay, cool. And plus, like for the follow-up, do you guys have plans to come up with the next series of the open models from AI2, like the open series?
Yeah. So the Olmo, we're training the next generation of Olmo. I'm hopefully going to be contributing to the post training of that.
Okay.
And in the meanwhile, there's been good work from other labs. Specifically, kind of there's some good research from ServiceNow and from Ant Research on kind of fixing another issue that everybody just kept coming up to talking to me about this ICLR poster. Everybody had the exact same question. They're like, we're doing long chain of thought, and we don't want to wait until the whole batch of generation is finished, because there's like, you look at that like little graphic on the left, like there's just like one chain of thought that's going all the way to the end. And so this, like, you want to be even more async. And so there's these kind of two pieces of research that have been great at getting more async around even like within a batch. So you kind of, ServiceNow calls it in-flight updates. I think Ant's research paper is called a reel, and the idea that you just like, do an update on the data you have and then keep generating. And the crazy thing that ServiceNow's paper does is they update their model weights halfway through a generation, and it just works. That's kind of fun.
So from Ant research, I haven't got to this paper yet. Well, take a look.
Yeah. So
Hey, Michael, I had a question.
Yeah, go ahead.
Great presentation, by the way. But like, I'm still an undergrad, so most of the things went over my head. So like, even I'm trying to like break into the field of post-training architectures and RL and alignment techniques. So like, how do we like get started in this field, given that the pace of innovation has like gone out of the roof? How do I like get started with stuff?
I don't know if the pace of innovation, I think the innovation is happening. We just don't necessarily know about it because it's not being published. I think if you want to work in post-training, I think understanding the basics of RL is really good. So kind of having that background in kind of at minimum policy gradient methods. And then the other part, I think, is understanding kind of the current issues with post-training and kind of the challenges that people are trying to tackle. I think a lot of the times there's been really good papers that have been just understanding what's really going on in these models without actually necessarily using huge resources. So I'm thinking of like, this isn't exactly post-training, but there's a fantastic paper called the 4 highly effective habits of self-taught reasoners that try to understand like, we're supposedly learning this reasoning from just post-training, but what is reasoning actually, and understanding things from like a cognitive science perspective, and saying like, oh, you need to see these sort of cognitive habits in your pre-training or SFT data in order to be able to do reasoning. So there's kind of this really interesting aspect of like a cognitive science approach to how to do post-training. There's kind of the purely engineering sort of stuff of kind of how can we do asynchronous RL. I think the best thing to do is, if you have the resources, just reproduce some some existing results. I think the tiny zero repo of doing like R10 on Countdown, that was a great thing to do. And then understanding how different pieces there interact. It's a little bit difficult to work on the state-of-the-art engineering stuff if you don't have like a cluster of GPUs. And even if you do have a cluster, to be able to like reserve multiple and to look at asynchronous stuff is difficult. But I think there's still so much to be done on the real basics of data, kind of stability of algorithm and objective, and the understanding of what is the actual way that we achieve capabilities in our models through post-training. And like, what are the prerequisites to achieve those capabilities? I don't know if that's...
No, cool. It's cool. Again, a follow-up question. I don't know, it might sound very naive. So like post-training architectures and the innovations that are going on now, is it primarily in the architecture, or is it more efficient use of GPUs and hardware?
There's a lot of papers that are just making small modifications to GRPO. And I think that those papers, I don't know if those papers will stand the test of time, to put it lightly. But I think, and there's a lot of papers that are trying to make these kind of, bring the kind of rich RL literature from deep RL into LLMs in RL. And that sort of stuff, I think there's a lot of room for that.
So in the architecture?
Kind of in the architecture, in the paradigm, I think is a better way to do it. But
Yeah.
this will then like affect the objectives that you can work on. And then there's also like a very nascent field that's just looking at like optimization for RLVR and RLHF, because like everybody's been using Atom, but like pre-training has moved on to some of these interesting second order methods, and I think that post-training could really benefit from that as well.
Cool. Thank you.
Yeah.
And all the best with your upcoming works.
Thank you. So,
Yeah,
that,
I guess so. Oh yeah, sorry. Was there another question?
no, just respond to the chat. There's a question from the chat on what does your research workflow look like for staying on top of the latest work? Do you rely on archive, internal lab discussions, or something else? I try to stay on top of some of the latest work, but I think it's like physically impossible to stay on top of all of the latest work, and I don't think it's actually useful as a researcher. As an engineer, sometimes it is. But I think if you're constantly looking at just the latest research papers, the ideas that you're going to have are going to be kind of just a little bit ahead and not actually very far ahead. And like when I wrote this paper on asynchronous RLHF, like the infrastructure for asynchronous RLHF wasn't built. That's kind of the impetus for writing this paper, was the fact that I got scooped on the previous paper. And I was like, I can't just do something that's going to be a little bit forward. And I think that if you're just reading the latest work, that's kind of in the latest work in your specific field, it's kind of not helpful for coming up with research ideas that are going to go a lot forward. So I try to keep up with kind of research, not just in my field, but research in other fields as well, like their latest work and kind of the interesting papers from around kind of all of, LLMs and deep learning. So I've been reading a lot of interesting stuff on like text diffusion models, some stuff on representation learning, things I haven't done that much on like more mathy optimization stuff, but yeah, like the optimization work, like soap and shampoo for pre-training. Those things have been super interesting, and like getting you to understand the general field as opposed to just like your particular subdomain.
If I might interject, as like you mentioned, right? I think just engaging in regular paper reading is probably a better practice for engineers, because well, if you're working on a long-term research project, there's no point kind of chasing what people have been working on for the last 6 to 9 months, right? So like I really appreciated what you said about being like kind of forward-looking as someone who's doing like meaningful original work. But as a knucklehead, I use this service. It's called AlphaKive. It's kind of like I would describe it as like TikTok for archive papers. So it's a recommender system that you can customize quite a bit to see what's been going on recently. I think the other thing that you can do is find researchers that you like, or like that you've attended their talks or something like that. Follow them on Twitter or Blue Sky. That if you make a separate account that's just like ML papers and gets rid of the rest of the noise, like that's very pure signal and shows you exactly what people are working on at any given time. And then this one is kind of a joke. This next recommendation of mine, but genuinely it's pretty helpful for me. So this is a Instagram account that does I guess like vertical video that does a quick TLDR, a minute or two, talking about a recent paper that's they normally tend to focus on kind of the landmark ones, like the ones that are introducing really like new methodologies, and not something that's like oh, we applied this to a new domain. But yeah, it's narrated by an AI Peter Griffin, and there's like Minecraft stuff in the background. So if you have if you have TikTok brain rot and you that like genuinely, I have learned quite a bit from this account. So yeah, unconventional methods, I know, but we live in strange times.
Yeah, like whatever works for you, I'd say is the thing that you should do. He doesn't need it, but I'm gonna advertise Nathan's blog. So my manager here at AI2, Nathan Lambert, has a blog called Interconnects, and he does a lot of this sort of like reading on Twitter and everything, and I don't want to do that reading. I'm trying not to brain rot, but he'll collect kind of a lot of the more interesting works, at least kind of in this area of post-training, pre-training language models, and I find his blog posts to be like a good overview of like the recent stuff, and like interesting takes. I think that's kind of I think we're missing a little bit of that, of kind of people that don't just kind of tell you what these papers are, but give like a little bit of context, the way like a good journalist would. I don't know if we should have that in machine learning. I think the rise of influencers is kind of a weird thing, but it is what it is.
So, what was this paper on the left that you are showing up? The ServiceNow research paper?
Oh, that's it's not a paper; it's a blog post in a GitHub repo.
Okay.
You can find it on the Hugging Face blog if you search for pipeline RL.
Okay. Cool.
Yeah. Shout out Dima and the whole team at ServiceNow Research. They're also doing great open source work. and a lot of their stuff on using code permissibly was very prescient in today's landscape.
Mhm.
Michael, I love how you're opinionated but like kind of understated about research trends. So I kind of wanted to poke the bear a little bit. So obviously, you believe RLHF has a bunch of potential still, after all the, after everything, there's still more to dig there. Are there any, major research directions where you see, and like, I guess, where you think resources are being wasted, where you don't really, where you might have colleagues or that, that are working in a space that you don't think will, like you alluded to, some of these papers, maybe entire subdisciplines will not stand the test of time, right? So I guess, I know this is going to be a little speculative, but would love to get your take.
I don't know. This is the thing. Like, I think right now, anytime something gets really popular, I think a lot of people go into that space and then they do a huge amount of research that ends up being not necessarily, like, just exploring a lot of tiny directions. Like, I don't know if everybody remembers all the GAN papers that came out. I want to say in like 2017, 2018. It's just like a deluge of GAN papers, like all these different acronyms. And like nobody remembers most of those GAN papers. I think like 3 different papers kind of in their lineage kind of are the things that are remembered. So I think that whenever there's any hype direction, there's just going to be a lot of work that ends up being kind of incremental in not necessarily the important ways. And I think it's still useful to do that work. I just don't think it's the most interesting for me. I don't know, of my controversial takes, I'm not a big believer in mechanistic interpretability. The thing is, I have researchers that I respect deeply who have worked on that, and I believe them when they say it's like, okay, this is actually interesting. So, as someone who hasn't like read on that field deeply, like my outside perspective is that I don't think so. But smart people are working on it. Clearly, they see something I don't. And my counter to, I think, the thing that people should be looking at that they're not looking at is, I think what Marzi Ghassemi once called justifiable AI. Like, you don't have to explain things mechanistically, you just have to justify things in a reasonable way. And I think that aligns more with my perspective of how humans work. We're not explainable, we're justifiable.
Yeah, I've heard that phrased as like humans aren't rational but rationalizing. But yeah, I think we have a question from Mayank. Oh, actually, I think did Sarwar have his hand raised already? I'm sorry. You guys can like rock.
You can continue. You can continue.
Okay, yeah. Can we have Mayank go and then Sarwar?
Yeah. So like I was browsing through both Ants and ServiceNow repositories and research, and what I'm looking at is like it's purely like it has evolved into an engineering heavy discipline right now with async RL and like SGLang and your all sort of inference libraries that are being used. So like what do you think, like will this be evolved in the implementational or the efficiency side, or the implementational aspect of like more trying to gain performance, or like you alluded to earlier, will some mathematical new method will come up, will that will kind of revolutionize the game?
I think so. Yeah, this is kind of like, I think the point of the the talk in the paper is that it's kind of a coevolution, that we
Mhm.
have advances. There would be no async RLHF without VLLM. And I think that async RLHF is going to create the need for the next features that VLLM will implement. Like there's already, like, since we implemented the paper, and there's been new kind of sort of async libraries like Merle and hybrid flow. We've started to see all these issues and these contributions to VLLM that are aimed specifically at RLHF. And that's kind of the thing that happens. You know, you come up with ideas, and the infrastructure and the algorithms co-evolve. I think the important thing is to co-evolve a little bit intelligently to kind of consider the things that you're doing.